Yes. Yeah, so we'll be going over how to implement convection codes in 2D. So you're going to need MATLAB. And actually, I posted up some starter code onto Canvas as well. And so if you go to the page for week 6 on the Canvas site, the very bottom file down there is the starter code for today's activity. I also uploaded, so I realized I forgot to upload the solutions to our activity last Monday for 2D diffusion. And so I've uploaded that as well. So you can use that, because if you're struggling with problem 3 on the homework, then that code should help you out, at least in implementing the boundary conditions. Because I know we didn't finish implementing all the boundary conditions. So you can check out that posted solution and see how that's done. You can just submit all the files individually. So if you can submit just a PDF at each of the individual PatMap files, that should be fine. That's usually most convenient because in Canvas, if you upload them as separate files, and I can view them within the browser. So that would be good if you can do that. Yep. Yeah, you can upload a lot of different files. Yeah. Last semester, I had one guy, like if it was a homework assignment that took him like 7 or 8 pages, he would take individual photos of each page and upload them as a JPEG image. But the thing with Canvas is they can't view JPEG images, so I had to download each individual image, which were all out of order, by the way. And then I tried to make heads or tails of what he was doing with his homework. So that was not fun. But if you upload all your files and they're adequately named, then they should view in order. Oh, I see. I see. Yeah, Canvas, you can upload multiple files, and then it's all part of the same submission. Mhm.
sorry, I didn't hear earlier. We are using MATLAB today?
Yeah, we are using MATLAB. Yeah,
Um,
and there's a starter code that's on Canvas as well. So if you go to the page for week 6, at the very bottom of the page, you'll see starter code for convection diffusion class activity, and we're gonna work on that one today.
cool. Thanks.
Mhm. Yeah, if you're struggling on problem 3 on the most recent homework, I posted up the solutions to the activity that we did last Monday for 2D diffusion. And so if you're struggling with computing the boundary conditions, because I think we didn't finish that up, you can look at that solution and see how that's implemented.
Hey, Professor, I had a quick question.
Sure. What's up?
Yeah, regarding one of the homework problems, it's more, I guess, my curiosity when you're plotting the computation time versus the grid size.
Mm-hmm.
I guess because I did the polyfit and I did the exponential fit.
Mm-hmm.
So to me, it looked like the third or second order. They kind of look the same
Mm-hmm.
for the polynomial, but like I guess the basis of would that have something to do with I guess how the computation is it doing like 2 times like x squared amount more computations every n you add or every
Yeah. No,
okay
that's exactly it. So when you increase the size of the domain, like you're increasing it in both directions, right?
yeah
So like if you double the amount of nodes in each direction, then you're multiplying the number of nodes overall by 4, and so that's why you kind of
yeah
an x squared increase. That said, though, in practical cases, you won't see as nice a fit like that because there's other things that are in play as well. And so like probably one of the bigger aspects is the amount of fast access memory that you have or how much RAM that you have. Because the bigger your problem size is, if your problem's too big to fit on your RAM, then your computer needs to use some that's more like its hard drive space, and that takes
oh
longer. That takes longer to access. So usually, it's about x squared up to a certain point, and then once you get
okay
past that, then it shoots up even more just because it has to use memory outside the RAM.
no that makes sense
Mhm.
thank you
Yep. Okay. Oh, starter code. So the file name should be, let me see, 2D convection diffusion class activity starter code. Yep. Yep. So the actual file name is EGME 417 2D convection diffusion finite difference starter. So quite a mouthful. Yeah, but it should be at the bottom of week 6. Mhm. Okay, it's 5:30, so let's go ahead and get started today. All right, good evening, everyone. How's everyone doing? Midterms this week? Busy? Yeah, it's that time. Yeah, I know our midterm is next week, so so at least for this class you don't have to worry too much. But I know probably you guys have a lot of other midterms going on. Yeah, but as long as you make it day by day, that's the most important thing. Okay, and so today the plan is to finish up our lecture notes on convection. And so part of this, we're going to do a class activity where we implement a 2D code together. And so class structure wise is going to be very similar to what we did last Monday with the 2D diffusion code, except this time we're going to be adding convection to it. Okay, and so there is a starter code that's posted on Canvas. And so if you go to week 6 of our Canvas site, then at the very bottom you should see a starter code for convection diffusion 2D class activity, something along those lines. Okay. And so, we'll probably get to it maybe about 30 minutes into the class. And so, I want to spend a bit of time developing the equations and recapping a bit because it's been a while since last Wednesday. And then we'll probably work on that MATLAB code for the majority of class. Okay. And so besides that, we have a homework that's due tonight. So homework's due tonight. And if you're struggling with problem 3, so I got a few questions about it over the weekend. I just realized today, actually just 30 minutes ago, that I never posted the solution from our class activity from last Monday, because I don't think we ended up finishing that. And so if you're struggling with applying the boundary conditions for problem 3, 3A, and 3C, I posted a solution to our activity on Canvas. And so that's available for you as well. So, if you're struggling with that, definitely take a look at that, and hopefully it'll give you some points on that. But with that said, I know it's a busy week for everyone. So, if you have midterms coming up, just don't worry about it too much. Remember, because this class, the homeworks are graded on completion, and so as long as they can see that you gave it a good effort to implement the homeworks, then I'll give you full credit for that. So, since I know it's kind of an impacted week, just kind of submit what you have, and then I'll give you feedback on your homework. So then you can use that feedback for the midterm. But if you have other things you need to do this week, then definitely prioritize those things. Okay. So are there any questions that I can answer before we get started?
Just one question regarding the midterm and the format. I might have missed it.
Yeah, I'll talk about that next. Yeah, that's
Okay,
kind of the first
okay.
thing. Mhm.
Thanks.
Mhm. I was stalling for a little bit because I know people kind of roll in about 5 minutes into the lecture, so I want to make sure everyone hears the midterm information. Okay, so let's talk about the format for the midterm then. All right, so the midterm is going to be next Wednesday. Okay, and the date for that, I believe, will be March 10th. Okay. And the midterm will take place during the class time. Okay. And so the time for the exam will be 5:30 to 7 p.m. So normally our class ends at 6:45, but I'll give you another extra 15 minutes because I know scanning and uploading documents takes some time. Okay. And so the midterm exam will be based just purely on the theory. Okay. Theory and the equations. So there's going to be no MATLAB. Okay. And so this is typically what I do for the exams, because I know for these exam periods it's time limited things. So I don't want people to be debugging their code in the middle of the stressful time like this. So I just want to focus on just developing the equations. And so basically what I'm gonna expect you to do is I'm gonna give you basically a differential equation. I want you to apply finite difference to it, and then I want you to develop basically the set of differential equations or the set of algebraic equations that govern its behavior. So very similar to what we've been doing in the lectures. And then on your next homework assignment, the one that I'll assign after tonight, you'll get some additional practice doing that as well. Okay. In terms of number of questions, I'm going to have 3 short answer questions. Okay. And so for those questions, you're just going to type up your answer into the browser, and so you don't have to write anything. So hopefully that will save some time. Okay. And then in addition to that, there's going to be 2 more problems. And then for this class, you can think of them as like finite difference problems. Okay. And so those problems will be kind of exactly as I just described. So, I'll give you a differential equation. It might have diffusion, it might have convection, it might have a source term, and I want you to develop, say, say we have 16 nodes on this grid, maybe a 4x4 grid. I want you to write out all 16 equations that govern that equation, okay, for each of the 16 nodes. So there's that, okay. Since it's going to be a virtual exam, you can use any of the notes and any of the lecture videos that are available to you. Yeah. Yes. So 3B. Yes. So 3B is a great example for what I would expect you to do for the exam. Mm-hmm. All right. So it's going to be open notes. We don't really have a set textbook, but if you got one of the textbooks, you can use that as well. I'm not really following the textbooks all that closely, but you can use that. Okay. Right. YouTube is available to you too, so you can use my lecture videos. Right. I wouldn't recommend it though, because you only have an hour and a half, and you don't want to be sitting there watching a lecture for 20 minutes of it to try to answer one question. But if you know the exact timestamp for what you want to look at, there's that's available to you too. Okay. Okay. And of course, you can use any of the posted homework solutions or posted codes to help you out as well. Oh yeah, you can do that too if you really want. Yeah. Maybe so, but don't take that as a challenge. What was I saying? Oh yeah, open codes too. And so even though you're not going to, MATLAB's not required for the exam, you're free to use it if you want to check your solutions. I don't think you're going to need it, but if you want to use it, that's available to you as well. Okay, so the only thing I ask is that these exams are an individual effort, right? So the unfortunate reality of teaching a class is that the exams I need to kind of assess you guys individually. So in order to do that, you can't talk to anyone else in the class, right? And so during that 90-minute period, I don't want to see no activity on the Discord server, and and definitely don't talk to your friends, during the exam as well. Okay. And also, this was a big problem I had last semester too. This also includes, asking for help from people outside the class too. So I had a lot of issues last semester with, students posting the exam questions on Chegg and then getting help from there too. So obviously that's off limits as well. Right? Okay. No, please don't call me senpai. Please don't. I mean, you can if you want, but it's I prefer not to. But if you want to, you can. I will review before the exam. So and so tomorrow, what I'm going to do is I'm going to type up a study guide for you to help you prepare for the exam. And then on Friday, and then sometime later this week too, I'll release a poll for you to vote on the topics that you would like me to review for the exam. And then what I'll do is on Friday, I'll record myself giving a review session for about an hour 15 minutes, and I'll post that on YouTube, and I'll share that with you guys too. So during these review sessions, the way I typically like to do them is I like to go in depth with about 2 or 3 different topics. And so I don't have enough time to cover everything that we've done, but I at least want to cover the topics that people seem to be most uncomfortable with. So keep an eye out for the study guide, and keep an eye out for that poll, so that you can vote on the topics that you would want to see most from the review session. Yeah. Question. So will we need to solve a system of equations? No, you will not. So you will only just need to set up the system of equations. So I just want you guys to write out the equations, and that will be most of the points right there. Yeah. I might ask you a couple conceptual questions too. So I might ask you, what's the Peclet number and things like that. But you won't have to solve anything. Yeah. 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 So hopefully that will help as well. Okay. Let's see what else. Yep. So it'll take place through the browser on Canvas. Oh, so I'll open up the Zoom lecture next Wednesday during the exam, but you're not required to come because it's a virtual exam. But if you want to come in and ask me questions on that on Zoom, you're free to do so. But I'll be available through email and Discord as well during that time period as well. So if you want to come in, that's great. So then you'll have direct access to me. But if not, you can ask me questions on Discord and email as well. Yeah. Mm-hmm. Okay. So any questions about the exam format? Okay. Yeah. So for this class, I'll be the first to say that for a class that heavily uses MATLAB like this, it is a bit strange to do an exam because the exam doesn't exactly reflect kind of the majority of the work that I think that we do, which is implementing code in MATLAB. But knowing the theory is extremely important because knowing the theory and really understanding that is a big part of writing good code as well. And so it might seem a little bit strange to have an exam without MATLAB, but you know, I think it's a good way to kind of test if you really understand kind of the underlying theory for that stuff. Okay. Review. So the review is going to be pre-recorded, so it's not going to be in the lectures, but I'm going to do it on Friday. And so what I'm going to do is after I get the poll results, I'm going to basically just, you know, open up a Zoom room just by myself, record the review session, and then post it on YouTube. And so you'll have it. You'll have it before the weekend, so you can use it to help you study over the weekend. Yeah. Mm-hmm. Okay. Any last questions on the exam? Okay, so let's go ahead and pick up where we left off last week then, right? Right, and then so if you remember from last week, we were going over convection problems with finite differences. Okay, and so if you remember from last week, you know, before we did the last lecture, all we've been doing up to this point, which is just was just diffusion equations, right? And so diffusion is characterized by a passive spreading of our material. And so, you know, that could be temperature, you know, it could be heat, it could be a mass transfer, right? And so diffusion is just passive spreading out in every direction. Convection, on the other hand, is active transport. Yes, yes. So this is a continuation of lecture 6, correct? And today, after today's lecture, you know, this is the cutoff point for what's going to be on the exam. And so today's lecture will be on the midterm exam next week, but the next lecture will not be. So after today, you know, that's all you have to worry about for midterm 1. And so convection is characterized by an active transport. And the way that we do this is that we apply a fluid field. Okay. And so now we basically introduce a velocity into our equations, and that's going to help us, you know, transport our materials. Okay. And then through convection, we've been introduced to a lot of new numerical, a brand new numerical issue that can arise, and that's the issue of stability. Okay. And so this is separate from accuracy. And so stability is the, you know, or I should say instability is the tendency for numerical solutions to kind of do some crazy oscillations, right? Right. So stability is basically certain conditions right. Certain conditions must be met in order for our solution to be stable.
This is lecture 7, correct?
The lecture notes is 06, and so we're still doing convection finite differences. Okay. And so we saw last week that if we had an unstable solution, you know, it kind of did some crazy stuff, like maybe something like this, right? And so that's an unstable solution. And so obviously we don't want this because there's you know, not that many physical phenomenon that actually do this. And so I almost said none, but it's hard to say none because someone will be, oh, well, actually, you know, there might actually be something that actually does this. So I'll say almost none, but usually none. Okay. Right. And then we had two ways to basically make this stable. And so one way that we did this is we applied a central differencing scheme with a refined mesh. Okay. And because remember, you know, the issue with the central differencing scheme is that it uses information, it tries to use information from upstream or downstream, I should say, of the convection velocity. Okay, and in order to make the central differencing scheme stable, we had to we use this number called the Peclet number. Okay, and we had to basically make sure that our Peclet number was less than 2. And the way that we did that was we refined our grid such that delta x was pretty small. Okay? And so that's one way that we did it. The other way that we can make it stable is if we use a backward differencing scheme. Okay. And we use backward differencing scheme when the convection velocity went from left to right. Okay. And that made our solution stable at the cost of some accuracy. Okay, so you had kind of a trade-off that for either one. Okay? And so all of this was in 1D. And so what we're going to do today is we're going to apply all the same concepts, but we're going to apply them in 2D. Okay. And just because in 2D, we're going to use we're going to be going in different directions, not just forward and backwards. We're going to go up and down. Kind of the general name for these kinds of techniques where you use a lopsided differencing scheme to make it stable, this is known as upwinding. Okay. And so you'll hear me use the term upwinding throughout the rest of today, and all that basically means is using a lopsided differencing scheme to make a convection dominated flow stable. Okay. All right. Any questions on this? This is all just kind of recap from last week. Okay. And so now let's do this in 2D. Okay. And so as we always do, let's start with our governing equation. Okay. And I'll leave everything in terms of just kind of generic variables just so that we can work with that. Okay. All right. And so first we have our diffusion term. And so I'm going to use K to model our diffusion constant. Okay. Right. And since this is our diffusion term, we have second order derivatives. Right, so we have K times d squared phi dx squared plus d squared phi dy squared. And this is equal to the convection terms. Okay. And so we have u times d phi dx. And so that's the convection term in the x direction. Then we have v times d phi dy, and that's convection term in the y direction. And then we have our source term. Okay. Right. And so this equation right here is kind of the most general convection diffusion equation in 2D. Okay. And so what we're going to do at this point, just like we always do, we're going to apply finite differences to every single one of these derivatives. Okay? So now we have 4 derivatives now, and we're going to apply finite differences to all of them. Okay. All right, so let me use some color coding here just to kind of make things a bit more clear. And so let's start with the x derivative for the diffusion term. Okay. And so this is a second order derivative, and so we're going to apply our central scheme for second order derivatives here. Okay. And so you have k over delta x squared times phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, right? And so that's just our second order diffusion term, second order diffusion finite difference for the second order derivative. Okay. Next, we have the y derivative for our diffusion term. So this is going to be k over delta y squared, okay, squared times phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, okay, equals, right? And so that's our diffusion derivative in the y direction. Next, we have our convection derivative in the x direction, okay? And for now, what I'm going to use is I'm going to use central difference, okay? Because right now we don't know which direction u and v are going in, right? Because if we knew that u was positive, then we can use a backward difference. But remember what we talked about at the end of lecture last time, if u is negative, then we would use a forward difference. So, just in this case, since we don't really know, I'm just going to use a central difference and then just hope that we can refine the mesh enough to make it work. Okay. And so the central difference scheme for this first order derivative is going to be u divided by 2 delta x times phi I plus 1 comma j minus phi I minus 1 comma j, okay? And so that's our x convection derivative. Then we have the y convection derivative, and the same thing, we're going to use central difference, okay, plus v divided by delta y, 2 delta y, okay, times phi I j plus 1 minus phi I j minus 1, okay? And then finally, we have our source term, which we're just going to leave as qij. Okay. And so what we have here is, just the first step of what we get after applying finite differences to our 2D diffusion equation. Okay. And so obviously it's a mess. And so, we have a lot of terms here. And so, before we actually implement this in code, we're going to organize this a little bit just to kind of make our lives a little bit easier. Okay. All right. Any questions on any of this? Okay. Okay. And so, this is going to form the basis for our algebraic equations. But we need to kind of massage this a little bit, or we need to simplify it, just because right now it's kind of a mess. Okay. All right. And so in order to do that, let's go ahead and assume that our grid spacing is the same in the x and y directions. Okay. Okay. And then in place of either delta x or delta y, I'm just going to put delta. Okay. Yes. Yeah. So we use central difference for the purple term too. Mm-hmm. Okay. And so now that we've assumed that the grid spacing is the same, which is pretty reasonable for all the cases that we've been doing in this class. Okay. What I'm going to do here, just to kind of avoid the number of fractions that we have, is I'm going to multiply this entire equation by delta squared. Okay. Okay. And so let's go ahead and do that. And so we multiply by delta squared, then our diffusion term just becomes k. Okay. And then I'm going to combine the two diffusion terms right here. Okay. So we have phi I plus 1 comma j plus phi I minus 1 comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j. Okay. And so hopefully that looks familiar, because that's our diffusion term that we were working with. And so this is problem 3 on the last homework. Okay.
Professor, sorry, can you go to the last page really quick?
Sure. Mm-hmm.
Thank you.
Mm-hmm.
Thank you.
Yep. Okay. What's the heck is this? Oh, that's my J thing. Okay. And so that's our diffusion term, right? So I just kind of combined both of those. And so the only common term we had between those was phi I comma j. And so that's why it became a -4. I'm going to move the convection terms over to the left-hand side of the equation. And so I'm going to take it from one side and subtract it from the other. Okay? And so our first convection term is going to be u times delta divided by 2. Okay. And then we have our phi terms in here. So this is phi I plus 1 comma j minus phi I minus 1 comma j, right, minus v delta divided by 2. And then we have our y difference terms. We have phi I j plus 1 minus phi I j minus 1. Okay. And so all of these are on the left-hand side. Okay, so all this is going to be go into our left-hand side matrix. And on the right-hand side, we have qi comma j times delta squared. Okay. Okay. And so this formula here that I have boxed, this is the general finite difference, finite difference equation for 2D convection diffusion. And so you can use this equation, very similar to how we've used these equations before, in order to get a set of algebraic equations, that govern our convection diffusion. Okay, and so all you have to do is basically apply this at different values of I and j, and so that you can get your, you can get all your algebraic equations from here. Okay, and so I put it in this form because I put basically all the terms with phi on one side of the equation. Okay. And so basically the side with all the phi, that's going to go into our left-hand side matrix, okay? In other words, we're just going to pull out the exponents or the coefficients out in front for that. And then on the right-hand side, we have our source term, and that's going to make it into our right-hand side vector, okay? And I kept it general like this because, if we present it in this form like this, all you have to do is just plug in certain values for k and certain values for u and v, and then you can solve for any convection diffusion problem out there. Okay. Okay. And so you'll see in a little bit, how we actually apply this to code. But before I do that, let's talk about stability just for a second. Because remember, we used a central difference scheme here for both the convection derivatives, and so we run the risk of being unstable, right? And so remember, our stability criterion here is that the Peclet number has to be less than 2. But since we're in 2D, we're going to have a Peclet number in both the x direction and in the y direction. Okay. Right, so first let's write the Peclet number in the x direction. And so this can be u times delta x divided by k. Okay. And this has to be less than 2. Okay. And then we have the Peclet number in the y direction. So this can be v delta y divided by k has to be less than 2. Okay. Right. And so since we have two velocities now, we have to check basically stability in both directions. Right? And both of these have to be less than 2 in order for us to have a stable solution. Right. And so if one of them is less than 2 and the other one is greater than 2, then we're probably going to have an unstable solution. Okay. All right. Any questions on this before we set up the problem for code? Okay. All right, and so let me first state the problem that we're going to solve in code, and then we'll actually implement it. Okay. So actually, this is a continuation of the activity that we did last time, except we're going to add convection, and then we're also going to change the boundary conditions as well. Okay. And so our grid is going to look like this. Okay, and so we have our square grid, but just so that you can easily kind of interpret what's going on, I've changed all the boundary conditions to Dirichlet. Okay. Right, and so on the left side, you're going to have a Dirichlet condition of 50. Okay, so the solution is going to be equal to 50 there. On the top as well. So on the top, we're going to have our Dirichlet condition equal to 50. On the bottom, we're going to have our Dirichlet condition equal to 25. And the right-hand side, right-hand boundary, we're going to have our Dirichlet condition equal to 25 as well. Okay. Okay. And so besides that, everything's going to be the same. But actually, let me actually define what the parameters are. Okay. And so for this problem, we're going to use a diffusion coefficient, which is equal to 3. Okay. Our value of u is going to be 30. Okay, so this is convection velocity in the x direction. Okay. And then v is going to be 75. Okay. And so our velocity vector looks like this. And so our velocity vector is basically 30, 75. Okay. And so visually, if you drew an arrow about this, it's basically an arrow that looks kind of like this. And so it's predominantly going upward because we have a stronger y velocity, but there's some horizontal component too as well. Okay. And so visually, you can think of it as like a wind current, or maybe like a water current that's flowing through our domain that looks like this. And so in addition to diffusion, what we have is an active transport that's going on in kind of this kind of vertical direction like this. And it's just going in that slanted direction. Okay. Okay. Any questions on this problem setup before I switch over to MATLAB? And so if you want to follow along, I posted the starter code on Canvas. It should be at the bottom of the week 6 course outline page. But if you just want to, sit and watch and then, review the video later and then implement it yourself, that's totally fine too. Okay. Okay, so let me go ahead and bring up my laptop here. Okay. Okay. And here is the starter code. So if you download the starter code from Canvas, you should see the following script. Okay. And so you can see it's structured very similarly to what we've had before, except the only thing is we have to kind of fill in a lot of these things. Okay. Okay. All right. So let's start by looking at kind of the top section here. The file is called EGME 417 2D Convection Diffusion Finite Difference Start. And so if you want to see where that's located in the course website, it's right here. And so here's our course website. You go to week 6, and then you can download this code right here. So it's 2D Convection Diffusion Class Activity Starter Code. So it's the last one on week 6. Okay, and so when you open up the script here, okay, you're greeted by this first section, right? So in the first section, remember, we always start with our variables. Right? Okay. And so just like we always do, so we're going to define the length, our domain, in the x direction, then the length of the domain in the y direction. Okay. And so both of those are just going to be set to 1. Okay. And then we define the number of nodes in the x direction, the number of nodes in the y direction. So we're going to set both of these equal to 50. Okay. And so we have basically a 50 by 50 grid that we're going to solve this. So fairly heavy. So it's, this is not a very light simulation. And I do that on purpose just to make sure that we can get a stable solution. Okay. And then from there, we can compute the total number of nodes. And so that's going to be, 50 times 50. Okay. And then we get 2,500 equal to that. Okay. And then we compute the grid spacings in each of the x and y directions. So all this is fairly standard from what we usually do. Okay. Right. And then we also define our left-hand side vector, our left-hand side matrix and right-hand side vector. Okay. And so those are okay, right? And then from here, we're going to define our problem constants, okay? And so we need three variables for this. We need one variable that lists out or stores our diffusion coefficient. Okay, so actually this is diffusion. I had my mind on fluids earlier, okay? And so just like we said, so this is our diffusion coefficient of 3, and so this is our value of k that we were mentioning before. Okay? All right, and then we have our velocity in the x direction, so this is 30, and so this is our u here. Okay? And then we have our velocity in the y direction, which is 75, and this is v. Okay, and so you can see here, I've already populated a lot of this code for you. And so the main thing is we're going to need to fill in, what's inside these loops, okay? Because we already kind of talked about, these loops last time. So I don't want to repeat that information. And I just want to kind of focus on just what's new for the convection code, right? And so before we start launching into this section over here, are there any questions that I can answer? Okay. Okay, and so let's start implementing this code, right? And so first thing we need to do is we need to populate the left-hand side matrix for all of the interior nodes, okay? And so if you go back into your notes, right, and we basically have this equation here. So this is kind of the last equation that we had in our notes. We basically want to implement this into code, okay? And so we basically want to establish each of these coefficients, and we want to put them in the correct places, okay? All right, so the first thing that we need to do is we need to compute the ID numbers for all of the, this node, the IJ node, and also all its neighbors. Okay? And so this is the same as what we did last week for diffusion, okay? And so we're gonna have 5 lines of code to write here. And so we're gonna have, we need to compute the ID numbers for this node. We need to compute the ID number for our left neighbor, our right neighbor, our upper neighbor, and our lower neighbor, okay? And so for this, just like we did for diffusion, we're going to use our ID equation, okay? And so we're gonna have my ID is equal to nx times j minus 1, okay, plus I. Right? And so that's our equation for my ID, right? And remember, the reason we do this is because, right now we're visiting the nodes in kind of IJ notation, but in order to incorporate this into our left-hand side matrix, we need to compute its unique ID identifier. Okay, so that's my ID. Next, we have left ID. So this is the ID number for the left neighbor. And remember, the left neighbor has the same j coordinate, and so we're going to have nx times j minus 1 plus I minus 1, right? Because the left neighbor has a value of I, its I value is minus 1 compared to the current node. Okay. And then let's now compute the ID number for the right neighbor, and so this is going to be nx times j minus 1 plus I plus 1. Okay. Right. And so instead of I minus 1, we apply I plus 1 for this case. Okay. Next, we need to compute the ID number for the upper neighbor. So I'll call this up ID. Okay. Right. And so the up neighbor is the j coordinate for this is plus 1 compared to the current node. And so we're going to do j minus 1 plus 1. Okay. And so you can simplify this and just say that this is just j, okay? But I'll leave it as minus 1 plus 1 just to kind of illustrate it. Okay? It's me plus I, okay? And then for the lower neighbor, we're gonna have nx times j minus 1 minus 1, okay? Because our below neighbor has a j coordinate that's 1 less than our current one, okay? And then our I value stay the same, so it's just gonna be plus I, okay? All right, any questions on the ID numbers here? So this is just kind of what we did last week with the 2D diffusion code. Okay. All right, and so now let's make our contributions to the left-hand side matrix, and let's split this up. Okay, as you can see, I've kind of split this up into I've kind of separated this into 3 different components actually. So actually, let me make another set of comments here, right? And so for this first one, we'll make this the x convective components. And for this one, we need the y convective components. Okay. And then for this, we're going to use central difference. Okay, but let's start with diffusion. Okay, so that's what we had before. And so we basically need to implement these coefficients into the left-hand side matrix. Okay, and so you can see that we have the K that's kind of distributed all throughout. Okay, and we need to make contributions to 5 different phi values here, right? So we have 1 phi, 2 phi, 3 phi, 4 phi, 5 phi, right? And so we're going to need all our neighbors for this one. So we're going to need the left neighbor, we're going to need the right neighbor, we're going to need the lower neighbor, the upper neighbor, and myself. Okay.
Hello?
Hey, what's up?
Isn't up ID supposed to be, I mean, or why is up ID j minus 1 plus 1?
Because compared to my ID, so this is kind of the base case right here, right? And so the base case, we have a j minus 1 kind of already ingrained into that. And so compared to this one, we're going to have j minus 1 plus 1 because the j coordinate is 1 above our current node. Yeah. So that's why I've added kind of a plus 1 here to kind of modify off the base case. And then for the lower ID, I added a minus 1 here to kind of modify that off the base case as well. Right? Right, so let's do the left neighbor first. So we're going to modify, remember when we're modifying the left-hand side matrix, we want to stick all on the same row. And so that's why you'll see me use my ID for the first coordinate here. Okay. And then since we're modifying the neighbor for the left ID, we're going to go to the column for left ID, right? And so we're going to do left-hand side matrix at my ID comma left ID. Okay. And this is equal to, according to this equation right here, it's going to be equal to 1 times K. So it's going to be 1 times diffusion, right? Because remember, diffusion is holding, this diffusion variable here is holding the value of our K coefficient here, okay? And so that's why we have that. Okay. Right, and so next we're going to modify the left-hand side matrix for the right ID, okay? So for the right neighbor. And so same as before, we're going to do left-hand side matrix and parentheses my ID because we want to be on the my ID row. And then comma right ID, okay? And then just like before, and just like the previous line, it's going to be 1 times the diffusion coefficient, okay? So it's 1 times K. Right, so next let's do the lower neighbor. Okay, so the lower neighbor is, same coefficient as before, so it's going to be 1 times diffusion. But then we change the column here for down ID. Okay. Right, and then we're going to change the one for the upper neighbor right here, and this is also going to be 1 times diffusion. Okay. Okay, and so that takes care of all the neighbor terms, and now we need to do this -4 for my ID, right? So we do left-hand side matrix at my ID, comma my ID is equal to -4 times diffusion. Okay, and so we're simply just extracting out the the coefficient in front of this guy. So it's -4 times diffusion. Okay.
So your first 4 left-hand side, the left, right, down, up, are just your first 4 phis.
Yes, exactly. Yep. Mm-hmm.
All right. All right.
Mm-hmm. Yeah. And so this, I actually like this quite a lot better too, because if you remember from when we did the 2D diffusion, what we did was we divided the entire equation by K. And so all we had here was like 1, 1, 1, 1, -4. But this makes it a little bit more explicit, just such that, we keep K on this side of the equation. And that's why we don't just, put in just integers here. We actually modulate this according to the diffusion coefficient. Yeah. And so this is actually pretty close to what I would expect you to do on the exam as well. Okay, so any questions on this so far?
Except on the exam, we would write it out, right? We wouldn't.
Exactly, right. Yep. So on the exam, you would basically just take this equation right here and then just start plugging in values of I and J into it.
Professor.
Yeah.
Wouldn't it be easier to just make like the ID functions like anonymous functions and then call them?
Yeah.
How the fuck? Oh.
Yeah. No, that's a good point. And so you can save some lines of code here if you want to make this into a separate function. And so actually, that's actually a good point too. If you're using Python, that's actually really easy to do. But in MATLAB, it's a little bit more annoying to do separate functions. And just for this too, because this is kind of our first time doing a convection code, I want to have all the code kind of in one place so that, we're not referencing different functions and different files too. And so for this, I'm keeping it all just in kind of, in one code like this. But for your own codes, if you want to write a function to compute ID numbers, that would definitely be a more efficient way to go. But for this, I just kind of want to lay it all out just so that, we can kind of see everything happening in real time. Okay. All right, any other questions on this before we start implementing the convection terms? Okay. And so now that we've done diffusion, now we need to start implementing the convection terms, because these guys are also going to make contributions to our left-hand side matrix, but they're outside of the diffusion term right here. Okay, so this is uncharted territory for us. So we haven't done this yet. Okay. All right, so let's start with the X diffusion term. Okay, and so there's only 2 of them here, so we're going to have 2 lines of code. Okay, so we're going to have left-hand side matrix and then left-hand side matrix. Okay. And so, because we only have 2 contributions here, we only need 2 lines here. And so we can see here that we need to make a contribution first to the right neighbor, because we have phi I plus 1 comma j. And then we need to make a contribution to the left neighbor, okay? Because that's phi I minus 1 comma j, okay? Right, and so we can actually reuse code that we used up here. And so let's reuse the code first for the right neighbor, okay? So we'll go ahead and copy this, paste it here, and then we need to use code for the left neighbor, okay? Just like that, okay? Right. And then we need to add these coefficients of u times delta divided by 2 into the left-hand side matrix, okay? But to do that, I'm gonna bring back something from our MATLAB review, which is our update notation, okay? And so if you remember this from our MATLAB review, remember, because right now we're making basically several different changes to the left-hand side matrix, right? And so what we want is I don't want to overwrite what I've already written here, because we've already assigned diffusion to the right ID, but I want to add to it, okay? And so to do that, I'm going to basically put this segment of code here of left-hand side matrix of my ID comma right ID and put them on both sides of the equal sign, okay? And so what this is going to do, remember, is say this is the new value of this matrix entry that we want. This is going to be equal to whatever was there before. And so what I've highlighted here is the old value plus whatever is new. Okay. And then the new variable, or the new something new that we're going to add to this, is the x velocity, which is our u value, times dx, which is our grid spacing in the x direction, divided by 2. Okay. Right, and then we can do the same thing for the left neighbor as well. Okay. 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 And be careful with your signs here. So remember, there's a minus sign out in front here, and so this turns into a minus sign for the right neighbor, and then for the left neighbor we have minus minus, and so that cancels out and becomes a plus. And that becomes plus x velocity times dx divided by 2. Okay. Right. Any questions about why we did that?
Because you don't want to erase the old values. You just want to add onto it.
Exactly. Right. Yeah. And so we add this part here just to make sure that we don't erase or overwrite what was there before. We just want to add to it. Correct. Mm-hmm. Okay. And so now let's do the same thing for the y velocity. Okay. And so the y velocity, we have this term right here. Okay. And so you can see from the 2 phi terms, we have phi I comma j plus 1. And so that's our upper neighbor. And we also have phi I j minus 1. And so that's going to be our lower neighbor. Okay. And so let's go ahead and borrow this, this code here. Okay. So first we have our upper neighbor. Then we have our lower neighbor. And then same thing as we did for the X convection, we're going to use update notation. Okay. And then from this, we're going to subtract y velocity times dy divided by 2. Okay. It doesn't matter if you use dx or dy because they're the same in this case. Okay. And so same thing for down ID. Okay, and then we're going to add the y velocity times dy divided by 2. Okay. All right, and with that, that's that part is complete, and so we've basically added all the contributions to this to the left-hand side matrix according to this this equation right here. Okay, and so we started with something that looked really scary, and it was a ton of terms. But if you compare this to our 2D diffusion code, we really don't have that much added to it. We just have this these 4 additional lines of code that correspond to these these convection terms. Okay. All right, any questions on this? Okay. Okay, and so the next step is to apply the forcing function here, or the source function. And so for this one, I used the same one as before, but just for illustration's sake, I'm going to cancel this out because it's kind of easier to interpret the results when there's no source function. And so all I did for that was I just added a 0 here. Okay? So this should already be in your starter code, so you don't have to do anything here. Right? Okay, so let's talk about the boundary conditions. So actually, this will be kind of a good chance because we didn't quite get to finish this last time. Okay. Okay. And so in this case, we have Dirichlet boundary conditions or essential boundary conditions on all 4 of our boundaries. Okay? And so we have essentially very similar code that we're going to write here. Right? And so first, let's go ahead and apply the Dirichlet boundary on the Dirichlet boundary condition on the left side. Okay. And remember, when you're applying these boundary conditions, it's important to kind of keep in mind which I or j value that you're going to keep constant. Okay. And so for the left boundary, the one that we're going to keep constant is I, and the I value for that entire left boundary is going to be 1. Okay. And so when we compute my ID here, okay, because normally when we compute my ID, we're going to use the same formula as up here, right? So again, my ID is equal to j minus 1 times nx plus I. Okay. But since we're constrained to the left boundary here, instead of I, we're just going to plug in its fixed value of 1. Okay. Right. And so we're going to do that for every single boundary condition loop. Is that for every boundary condition loop, we have a different special case for either I or j. Okay. Okay. And so once you've established my ID, then the contributions to the left-hand side matrix is easy. Okay. And so in this case, we do want to overwrite what was there. And so in this case, we want to make it so that the diagonal entry is 1. Okay. Okay. Actually, let me just comment this code out since we don't need it. Okay. And then for the right-hand side vector at that row, we're going to apply the Dirichlet value. So this can be 50. Okay. And so actually, just to make sure that our code runs, you can go ahead and comment out the lines according to the forcing function as well. Okay, just because this one has b right here, and this should be right-hand side vector. Okay. Okay, and so that's our first boundary condition there. And so remember, when you're computing the boundary conditions, the key is to determine, what the ID number is based on the special conditions for I and j. Right, and another thing to note is that just to make sure that we don't count the corner nodes twice, we loop over this, go from 1 to ny minus 1, just to make sure that we stop short of the corners. You need to comment out lines 51 through 60. So there's a section right there that says apply the forcing function to all the nodes in the mesh, and you want to comment that section out.
Why do we comment that out?
Because we don't need the source function for this problem, and so we're going to assume this q here is 0, and so we comment that out just to enforce that to happen. Yeah. Yeah. Okay. And so that's the boundary condition on the left side. Okay. So now we're going to apply the boundary condition on the right side. Or on the top boundary, excuse me. All right, and so just like before, we're going to type out the equation for my ID. Okay, so my ID is j minus 1 times nx plus I, right? And then from here, we're going to plug in our special value for either I or j, depending on which boundary that we're on. And so since we're on the top boundary here, j is going to equal to ny. Okay? So we're going to plug in ny in for this. Okay.
Is there a reason why for the left boundary you did nx plus 1 for the my ID?
Yes, because normally we have I right here, right? And so that's kind of the generic form for my IDs. We have nx times j minus 1 plus I. But since we're on the left boundary,
Oh, okay.
all the nodes on the left boundary have I is equal to 1. So we substitute 1 in for I.
Got it. Thanks.
Yep. And then same logic for the top boundaries. For the top boundary, everything on the top has a j value of ny. And so we're going to plug in ny in for j. Okay. Right, and so we're going to do the same thing as before since we have a Dirichlet boundary condition. So we're going to set the diagonal entry equal to 1. And we're going to set the right-hand side vector equal to the Dirichlet value, which is 50, I believe. Yes. Okay. Right. And then I'm just going to do the same things for the right boundary and the bottom one. Okay. The big difference here, and I think we kind of stopped short of this last time, is the bounds. Okay. And so for the left and the top boundary, we went from 1 to ny or nx minus 1. And so we stopped 1 short. And then just to kind of make sure that we don't apply the same boundary condition twice on the boundaries, for the right boundary and the bottom boundary, we're going to go from 2 to n. Okay. And this basically just makes sure that basically all the boundary loops stop kind of 1 short of the boundary. All right, and so just like before, we're going to compute my ID, but in this case, our I value for the right boundary is going to be equal to nx. Okay, and so we're going to have j minus 1 times ny, or nx, sorry, plus I. Okay, but instead of I, we're going to use nx. Okay, and then we're going to set our diagonal entry equal to 1. And we're going to set our right-hand side vector value equal to the Dirichlet boundary condition, which is 25 in this case. Okay. And I'm going to do the last sets of lines for the bottom boundary. Okay. And so for the bottom boundary, we have j is equal to 1. Okay. So let me write out the equation first. Okay. And so if we go ahead and plug in j is equal to 1 here, right? And that'll give us all the ID numbers for the bottom boundary. And of course, 1 minus 1 is 0, so you can just leave that out. But I'll leave it just like this, just so you can kind of see it. Okay. Okay. And so with that, that's all of our boundary conditions implemented. And so now we're ready to solve. Right? All right. So there are any questions on this? And so at this point, now we're ready to solve. And so I apologize. I should have revised this code a little bit more. Okay. And so in order to solve the solution, we have to do the backslash with left-hand side matrix and right-hand side vector. Okay. And so you can do left-hand side matrix backslash right-hand side vector. Okay. If we run this code, it's going to take a little bit of time because it's 50 by 50. And we end up with the following solution. Okay. Right. So for those of you who are following along, were you able to get this solution right here? Great, great. Yep. So this is basically diffusion in 2D. Okay. And so you can use this code as a reference for future homeworks. Oh, you didn't get it. Let me go ahead and finish the lecture, and then I can give you some feedback after the lecture. Okay. All right. And so now that we have a working code, or at least I do, and you will too soon. Okay. Let's go ahead and play with this solution a little bit. Okay. And so the first thing that you should do, and this applies to any code that you implement. Right? Oh, the file name is invalid. Okay. Let me touch base after the lecture. All right. Yeah, I'll touch base with you guys after the lecture. Okay. I see. Okay. Okay. And so the first thing that you should do whenever you get a working code like this is to try to break it as soon as possible, right? So that's always the fun thing. And so let's see if we can get an unstable solution, right? And so remember, we get an unstable solution if we increase the velocity, up by a strong amount, right? So let's change this y velocity here to 1,000. Okay. And so with this, our Peclet number will almost certainly be greater than 2. And what we should see is an unstable solution, right? And you can kind of see that here. And so you can see here that you can see our graph doesn't look as nice anymore. And what you can see here are these kind of almost like ripples on the near the top boundary. Okay. And so these ripples here basically tell you that, this is kind of the same thing as our unstable solution that we saw in 1D, right? So basically what's happening is that solution is kind of oscillating up and down. Okay. And so that's bad. So obviously we don't want to do that. And so if we do want to run a simulation with, with the y velocities 1,000, we either have to make sure that the grids are fine enough. So we might do 500 by 500. Don't actually do that because it might actually crash your computer. Okay, but that's one thing that you can try to do that. Okay? Another thing that you can do is you can, instead of using a central difference scheme here, what you can use is either a forward difference or in this case a backward difference to make sure that you have a stable solution. Okay. Okay. And so from here, I'm going to try one additional thing here. Is I'm going to crank up the x velocity as well, okay? And so the x velocity, I'm going to make this also 1,000, right? And so what's going to happen, and so what we have basically is a huge amount of velocity in the x direction and a huge amount of velocity in the y direction. And so what you would expect is that this solution would actually be really unstable, right? Because we have it really unstable in x and really unstable in y. But let's see what happens. Okay. And so what you see here is that that's not the case. And so you have a little bit of weird stuff going on at the top here, but largely this solution is actually pretty stable, right? And so it looks like, maybe the flag of some fictional country, maybe, but it's stable. But that's weird because we cranked up the velocities a ton, right? And so I can even prove this even further. So actually I can make this 10,000 and 10,000 right here. Okay. And you still get the same thing. You still get a stable solution, right? And so what's going on, right? Because what should happen is that because the Peclet numbers are so high, is it Bosnia's flag? I see. Since the Peclet numbers are so high, then you should get an unstable solution, right? And that's true. But in 2D cases, what you have is this additional thing called the cross-stream diffusion. Right? Oh yeah, sure. And so in 2D, what you have is, when you have two velocity components going on at the same time, what this can actually do, graphing partnership. What this can actually do is that this can actually create some additional diffusion into your system that wasn't there before. Okay, so it's a very strange phenomenon, and it's kind of a weird, unique thing. And so I think it's probably better if I explain this from my iPad. And so does anyone else want to see my code before I switch back to my iPad? Maybe the boundary condition codes? Okay. Yeah, I'll keep it here for just a couple minutes, and then we'll switch over to the iPad after that. Okay. Everyone good with the boundary conditions? Want me to scroll down a little bit? Okay. What do you know what number is on the side? And so what numbers do you see over here? 24. Oh, okay. Yeah, you have to make sure that that your boundary conditions are like this, right? So remember, for the left and the top, you are applying a boundary condition of 50, and on the right and the bottom, we're applying 25. And so if you apply 25 to all of them, then it's probably all going to be just one color. Yeah. Okay. I'll post this solution afterwards, so you can take a look. But I do want to talk about cross-stream diffusion. Oh, okay. I see. Yeah, let me. I'll take a look after, but I do want to cover cross-stream diffusion before we do that. Okay. Okay. Let me come back here. Okay. All right. And so what can happen sometimes, and this is, you know, both kind of it's mostly a bad thing, but it's also kind of unintentionally a good thing sometimes too, is you have some additional diffusion in 2D. Okay. Okay. And so what can happen sometimes in 2D situations with both basic convection and diffusion, depending on the direction of the velocity field, you can have some additional artificial diffusion. Okay. And so diffusion constant. Right, and so what you saw happening on my screen, oh, I see. Okay, yeah, I'll check it out after the lecture. Okay, and so the reason you know I was able to get a stable solution on my screen when I set, you know, u was equal to 10,000 and v was equal to 10,000, right? Right, because normally, you know, when we compute the Peclet number, which is u times delta x divided by k, and Peclet number is equal to v times delta y divided by k, okay? Right. Normally when we compute these guys, you know, and we have a huge velocity here of like 10,000, we would expect the, the solution to be unstable, right? And so what can happen sometimes is that when 2D, this diffusion coefficient on the bottom isn't the only diffusion that's going on, right? Right. And so what can happen sometimes is you can have an additional false or additional artificial diffusion that's going on, right? Okay. And this basically, and the reason this occurs, is because the convection velocity is not aligned with the grid. Okay. And so, you know, in 2D, what can happen is something like this, right? And so say we have our grid that looks like this. Okay. Okay. What can happen is that the convection velocities, you know, might look something like this. Oops. Okay. And so in other words, you know, the grid isn't aligned with the velocities, right? And at the worst case, it can be angled at a 45-degree angle in the grid, okay? Right. And so when this happens, you know, we have kind of an artificial diffusion that arises from just from this case. Okay, and the reason for that is, remember, when we compute diffusion, we're using finite difference schemes that are aligned with the grid, right? But when the convection is not aligned with the grid, we're kind of ill-equipped to do this, and it kind of has some adverse numerical effects. Okay. And so the reason I call this K false right here is this is like a false diffusion. So it's like a false God. Okay. So it's not real diffusion. So it's basically just a limitation of the method that we're using, and it's not really real. Okay. Okay. So any questions on this? Okay. And so I'll give you a formula for the false diffusion here. And so, you don't need to memorize this at all, but it's just to kind of give you a sense of how to actually compute it. Okay. And so the formula for K diffusion looks like, or K false looks like this. Right. So first you take the magnitude of your velocity vector. Then you multiply by the grid spacing in the X and Y direction. So delta X, delta Y. Okay. Then you multiply that by sine 2 theta. You take 4 times delta y sine cubed of theta plus delta x cosine cubed of theta. Okay. Right. And so you would never compute this, but the point I wanted to make with this is that false diffusion is maximized when theta is equal to 45 degrees. Okay. And by theta, what I mean is basically the angle between our velocity vector and our grid. Okay. And so if our grid looks like this, okay, and then our velocity goes like this, okay, theta would basically be this angle right here. Okay. And so when that angle is 45 degrees, then this false diffusion is maximized, and we get this kind of cross-stream diffusion effect. Okay. Okay, so at 6:45, I think I'll kind of pick this up next time, just because I know the end of the lecture today was a little bit hectic, just to kind of make sure that we all understand cross-stream diffusion, and then after that we'll start the next topic, which is time marching schemes. Okay. Okay, so thank you guys for tuning in as usual. If you want me to look at your convection diffusion code, you can stick around. But if not, I'm not gonna hold you guys here. So thank you guys for tuning in. Have a great evening, guys, and I'll see you on Wednesday.
Thank you,
Will
Professor.
you post the correct diffusion code, or is it going to be like up to us to like fix it and whatnot?
Yeah. The diffusion code from last Monday, I've posted the solution for that. And so that activity, the solution is there. I forgot to post it a little bit late. I just posted that before the lecture today. And then this one I'll probably post later tonight too. So you can look at just the solution for that. So if you want to just wait till I post a solution and compare with that, you can do that. Or if you want me to look at your code right now, I can do that too. Yeah.
Perfect. Thanks.
Yep. Mm-hmm. All right. So is there anyone